These are notes for 13.6. We'll be talking about some properties of summation and summation formulas. So we'll start here at the top with our properties of summation. So in the first property, you can see that k, constant, is simply brought out front of the sum. What this does is it leaves behind any term containing I, since I is kind of like the variable being used for the sum. I is what's changing here. So the a sub I term remains inside, and k, the constant, is removed. In the second property of summation, we see the sum of two I terms can be split up into the sum of each term individually. And that does work for sum or difference. So under summation formulas, what we have here is the sum from 1 to n of any constant is the constant times n. Next, the sum from 1 to n of I is n times n plus 1 over 2. This is the sum of the first n I terms. So if you're adding 1, 2, 3, 4, 5, 6, and so on, you would use this formula. The next one is the sum of I squared from 1 to n. So by plugging in 1, you get 1. By plugging in 2, you get 4. By plugging in 3, you get 9. So you're adding your first n square terms together. And then, of course, this last one, the sum from 1 to n of I cubed, is given. So we just need to be able to use these formulas to make some substitutions and then to evaluate. Okay, so we'll be doing that a little later on. We're going to start at the top here with a bound area region, and we want to approximate the upper and lower sums. So what this means is we're going to approximate area by using lower bound rectangles and upper bound rectangles. So in calculating an upper sum or a lower sum, what we'd like to do is find the overestimate or underestimate for the area under the curve here and above the x-axis. We're told to use rectangles of width 1 and the interval indicated for each problem. We're going to be working on problem number 24. We're using the intervals 0 to 5. And so with rectangles of width 1, we'll have 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. I'm going to start now with the upper sum for this area. I'm going to take that common width of 1 and factor it out. Remember, we're just finding the area of each rectangle. Every rectangle has a width of 1. And so factoring that out or leaving it in, I guess, wouldn't make much of a difference, since multiplying by 1 is not really going to change anything for us here. So let's do our upper sum. So what I'd like to do from 0 to 1 is choose the side of the curve that's highest. For that, since my curve is increasing from left to right now, using the right side would be the highest point. And so my upper sum, my rectangle here, will take its height when I plug in 1. That height, I'm going to estimate that it's about 4.5. From 1 to 2, my curve is highest when x is 2, and that height appears to be 5. Next, from 2 to 3, the highest point is when x is 2. So again, that would be a height of 5. For the fourth rectangle, the highest point is when x is 3. That would put me again at about 4.5 for this rectangle. And from 4 to 5, the highest point would be when x is 4, and that height of the rectangle would be 3. So we'll estimate this to be 22. So now let's take a look at our lower sum. To do our lower sum, we want to choose the lowest point on the curve. From 0 to 1, that lowest point would be at 0 when the height is 3. For the next curve, from 1 to 2, when x is 1, that would be my lower point. That would be 4.5. From 2 to 3, the lower point would be when x is 3, again at 4.5. From 3 to 4, the lower point would be when x is 4. That would give me a height of 3. And for the last one, the lowest point is when x is 5, the height there of that rectangle being 0. So this will bring us to 15. So this was my lower sum, and this was the upper sum. All right, so let's go on to the next section. So here we'll be finding the limit of each as n goes to infinity. I'm going to be working on problem number 32. So if I'd like to take the limit as n goes to infinity of 64 over n cubed times n plus 1, 2n plus 1, all over 6. What I'm doing with limits at infinity is comparing the highest power on the top to the bottom. So remember, fractions, when we have top heavy, my limit does not exist. Bottom heavy, the limit is 0. And if they have the same highest power, then the limit is equal to the leading coefficients. Leading coefficient over leading coefficient. So what's tricky about these problems is that it's in this factored form. So what we have to do is imagine multiplying it all out, what our leading terms would be. So in the numerator, I have 64 times n times n times 2n. So that would give me 128 over n cubed, sorry. And then in the denominator, 6n cubed. So since we have the same highest power, our limit exists, and we're just going to look at the ratio of 128 over 6. So we can reduce that by 2. To 64 over 3. And that's all we're doing in these problems. Okay, so we're going to need that as we work through these last few problems. So we're going to go down, and for the last few, I'm going to work on 2 problems here. We're going to start with a simpler one, and then we'll do one that's a little more involved. So the first one I want to take a look at, number 40. It says find the formula for the sum of the n terms, and then use that formula to find the limit. So what we're doing here is we're working inside with the sum first, and then the last thing we'll do is what we just did up here in problem 32. We'll find that limit. All right. So what I'm going to do is start with multiplying these 2 things in here together. So I want to continue to bring down my limit for my sum from 1 to n. We'll multiply the 2 things together. We get 4i over n squared. Now, one of my properties of sums back here at the beginning was this first one here. I'd like to take out everything that's not an I term. So everything that's not an I term is considered a constant k. And in this problem, that includes 4 over n squared. That's everything that's not I. So we're going to take that out of the sum. We're just going to put it here. So let's go on to step 2. This is now the limit. as n approaches infinity, and we take out 4 over n squared times, and now we go back to our sum. We have the sum from 1 to n of I. All right, so it's at this point we now use our summation formulas. So we had a sum formula for I, and it was this one here. So we're going to replace the sum from 1 to n of I with n times n plus 1 over 2. So this gets replaced with n times n plus 1 over 2. So that's really the first part of the problem here. Find the formula for the sum of n terms. Well, just about. It also includes the 4 over n squared as well. Okay, so all of that out front there, and then we'll just bring down our limit. Okay, so we now have all of this inside of the limit, and we can bring that together more if we wanted to, but honestly, we can just at this point work out our limit like we did in the previous problem. So if I were to multiply my leading terms, we have 4n times n, so that would give me 4n squared. And in the denominator, we have n squared times 2, which is 2n squared. So once again, with the same leading coefficients, my answer for the limit is the ratio of those leading coefficients. 4 over 2 is 2. And that's our answer there. Okay, so we did the two things it asked. We found the formula for the sum of the n terms, and that was this stuff inside. And then we used that formula to find the limit, and that was what we did here at the end. So we're going to do this one more time. We're going to scroll down here and try this with problem number 42. So this one has a little bit more going on inside, and that's okay. So we're going to start with, I'm going to start by multiplying this out. So I want to multiply that out. So I've got my limit as n goes to infinity of my sum. And so squaring this binomial, we get 1 plus 4i over n plus 4i squared over n squared, and then we still have that times 2 over n. In my next step, I'll multiply the two together. So I now have the sum from 1 to n of 2 over n plus 8i over n squared plus 8i squared over n cubed. So the next thing we're going to do is use our two summation properties to split up my sums. So we're actually going to start with this one over here and split them up. So we want to split up our sum into separate sums. And then what we'll do is work with this summation property to pull out all the constants. Okay, so step one, we're going to split them all up. So this means my limit as n approaches infinity is now the sum from 1 to n of 2 over n plus the sum from 1 to n of 8i over n squared plus the sum from 1 to n of 8i squared over n cubed. So now we're going to use that first property that pulls out all constants. And you'll remember a constant is anything that's not I. So the first one will pull out 2 over n. Then we'll pull out 8 over n squared. Then we'll pull out 8 over n cubed. So the first one will leave behind a 1. The next will leave behind I. And then the last will leave behind I squared. So I now have the limit as n approaches infinity of 2 over n times the sum from 1 to n of 1 plus 8 over n squared times the sum from 1 to n of I, and then we'll take out the 8 over n cubed, which leaves my sum of I squared. So all I've done is use my two summation properties. Okay, so I'm going to write those in. So this one was splitting apart. And then next, we took out the constants. And really, you could do both properties in one step if you feel comfortable doing that. So the next thing we're going to do is we're going to take each summation formula and replace it. So I have a sum from 1 to n of a constant. I have a sum from 1 to n of I, and then there's a sum for 1 to n of I squared. So I have those formulas back here at the beginning. Okay, so here's the one for the constant, the one for I, and the one for I squared. So we're using all three. Okay, so let's start in on those. So first we have the limit as n approaches infinity of 2 over n times, and here we go, the sum from 1 to n of a constant is the constant 1 times n. 1 times n is just n. Next, we have 8 over n squared times the sum from 1 to n of I. That formula is n times n plus 1 divided by 2. Then we have 8 over n cubed times the sum of 1 to n of I squared. That formula is n times n plus 1 times 2n plus 1 divided by 6. All right, so now what we have, this previous problem we did, it was just the limit as n goes to infinity of one big term. So we just evaluated that. Well, limits have the same property as sums in that you can evaluate the limit of each piece separately. So we're going to mark this. We're going to do the limit of each one of these separately, and then we can add them together. So the limit of 2 times n over n. So we have same highest power. My limit then is 2. Next up, we have 8n times n over n squared times 2. So on the top, that's 8n squared, and on the bottom is 2n squared. So same highest power, we get the leading coefficients, 8 over 2, which is 4. Last, we have 8 times n times n times 2n, which is 16n cubed. And in the denominator, we have n cubed times 6, which is 6n cubed. So one last time, we have the same highest power on the top as the bottom. And so 16 over 6, or we could reduce that by 2 to 8/3. Now, to find my limit, I just add these values together. So we'll make a common denominator of 3 here. So this becomes 6. This becomes 12. And added together gives us 26/3. And that's the value of our limit at the end. Okay, so that's a lot of work. You're going to want to make sure you give yourselves plenty of space, especially if you look at number 44. It's asking you to first cube the binomial. And then another thing you might want to note is that at the beginning, you could actually take the 2 over n all the way out of the sum, and then you can redistribute it in the problem later. So there are some different ways you can work through the problem if you prefer. Otherwise, I highly recommend you just stick with the method that I went through here. So I do like instead multiplying everything together first. So multiplying all the stuff inside the sum together first, that would be my first step. And then what we did after that was we started in on our sum properties, and we used both of them here. We split the sums apart, and we took out the constants. And if you want to do all of that in one step, you can. After that, I used the summation formulas to substitute into the problem. That way, you'll notice there were no more I terms remaining in the problem, and I could evaluate the limit using n as my variable at that point. All right. After that, we just used limit properties to add up the values. You should know that in problems like this, it is possible that you might get a bottom-heavy limit, and one of the limits might then give a value of 0, but you shouldn't reach a point where any limit is top-heavy. So you shouldn't be seeing this and giving an answer of does not exist.